So when I'm doing the trig limits, we're in section 2-4 on that back page that we didn't finish from last week. As I'm taking the limit as x approaches 0, what I can see from my Desmos graph is that as x approaches 0 from my left and my right, whether it's sine x over x or x over sine x, you can see here that my limit is equal to 1. So we can totally use that. To help us simplify this, because I've got 3 times x in my numerator, and I've got 2 times the sine of x in my denominator. And do you see x over sine x? So I know that's 1. So that means the limit as x approaches 0 is just going to be 3/2. How cool is that? I know. So let's scoot down and do example 8 while we're talking about it. The limit as x approaches 0, sine x over 5x. That's the same as the limit as x approaches 0 of the sine of x over x times 1/5. Are you okay with that crazy math? Because the sine x over x is what I know. The limit as x approaches 0, I can picture it in my head going up to 1, because I know this has a value of 1. So that means that my value there is going to be 1/5. Hey, the math is so easy after you see it. But when you're looking at it, if you're in that phase right now where you're getting so overwhelmed and freaked out every time you see a trig expression in your work, you kind of need to get over that, because sometimes they're so easy that they're right in front of you. All right, let's go back to Desmos. And when we go back to Desmos, we're going to look at turn off sine. See you later. And let's now talk about cosine. Do you see, as x approaches 0 from the left and the right, what is the limit of the cosine of x minus 1 over x? Do you see it? Do you see it? As x approaches left and right, it's 0, right? So now this one is a little bit different, because I can't just do the reciprocal, because the reciprocal doesn't work out. As x approaches 0, these two limits go off forever and ever and don't converge like the other one did. So the reciprocal of the cosine of x over x doesn't give us a limit. But what is interesting is we can take this limit that does work out, and even if we switch it around and have 1 minus, hold on a minute, I got to get over the 1 minus the cosine of x, notice that also converges at 0. So it's interesting that the reciprocal works for sine, not for cosine. But cosine does have 2 different properties that we can use when we're talking about how it works. Take a minute, turn to your partner, ask them, how are you going to remember this? See what they say. Go. Go back to what? Desmos? Okay. All right. So it's important to get these straight in your head, because when you're looking at them in just a context of a problem, we don't always recognize them. We don't always see what we're supposed to see. Okay, so let's talk about this one. I have the limit as x approaches 0, and I have x over, and you're like, how do I make it work? Sometimes if you know where you're going, you can kind of make sure you steer the bus that way. Who sees what I can do to get what I want? Yeah, factor 2 out. So if I take a 2 out, I've got the cosine of x minus 1. And we can think about this as 1 times that. All right, look at your sheet. Is the reciprocal of this one going to work? So what do I write? D and E, yeah. This limit does not exist because we saw the graph, how it goes on forever and ever, right? Just so we're all on the same page, step number 1 of all of these is always to plug it in. As cosine of 0, when I come over here and I'm looking at, okay, what is the cosine of 0? The cosine of 0, here's 0, the cosine is 1, right? When I go to plug this in, it would be 0 over 2 times 1 minus 2, and that's when I get that indeterminate form. Step number 1 should always be to plug it in. Same thing here. If we know that we plugged it in, 3 times 0 over 2 times the sine of 0, the sine of 0 is going to be 0. That's when we had that 0 over 0, which we know we're not allowed to have. Step number 1 in determining limits, no matter what, is to plug in that input value. This lesson is what to do when it doesn't work out in your favor. The limit as x approaches 0. What are we going to do about tangent? Is tangent on your sheet? What are we supposed to do about tangent? You cannot cancel out those x's. Go ahead. Yep. So you know that I cancel out the x's. Sine squared x over cosine squared of x all over x. Step 1, we should plug it in, right? Let's first make sure that it is a disaster. What is the tangent of 0? Right? Tangent of 0 is over, tangent of 0 is 0 over 1? 0. Plug in 0 in for x. That's where things went bad. I can't have 0 over 0. It's not even undefined. It's what we call an indeterminate. I can't determine it. Hey, sine of x divide by x is the same as sine squared of x over cosine squared of x. Instead of being divided by x, that's the same as times 1 over x. That's 5th grade. That's 5th grade. Oh my Lord.
my fifth grade.
That's good, great.
Sine squared of x over cosine squared of x divided by x. You okay with that?
Oh, that.
Instead of writing it divide by x, I'm allowed to write it divide by x. Are you good? We don't divide fractions because it doesn't work out evenly. We don't know what to do with all the pieces. So what we do instead is we multiply by the reciprocal. You okay there? Would you rather I rewrite it? That's the same as sine squared x over cosine squared x times 1 over x. If I get rid of what I did here. This divided by this is the same as this times this. That's 5th grade math. At Hutchison. Yeah. Ready? I can then pull out a sine of x over x, and then I can have the sine of x over cosine squared of x. The cosine of 0 is 1. The cosine of 0 is equal to 1. So this I can say is 1. The sine of 0 is 0. So this I can say is 0. Don't freak out about 0 in the numerator. 0 in the numerator is, say it. It's okay. 0 in the numerator, look Brady. 0 in the numerator is okay. 0 in the denominator? No. You're welcome. Hey, what's this? Anytime I end up with a 0 in the denominator, I got issues. If I get a 0 in the denominator, it's under 5. If I get a 0 in the numerator and denominator, I got to go back, pull out my algebra bag of tricks, and manipulate it so it works out. You're afraid of the sine and cosine functions, and they're the easiest ones to use compared to what we did last time. Last time, we factored, we found common denominators, we used the conjugate, we went nuts finding stuff out. Hey, on the back of your warm-up are these answers. So if you were one of my friends who wasn't here last week during this class, if you need to know the specifics of those math pages, I put that key there for you so you can check your answers. Okay? Now here's where Ms. Holdaway and I are starting to get a little nasty with your homework. We're just giving you the answer. We're not giving you the work. So that you can do the work and check your answer, and if your answer doesn't match mine, then you can ask a question and we can figure it out together. That's where the learning happens. So if you look on the other side of your warm-up that has a lot less writing, this is your homework for lessons 2-4. I'm happy to do a few for the people that did their homework. If you did not do your homework, you have the key in front of you, and my suggestion is to do your homework until you get it and you get it right. Because this is going to be one of the most important lessons, because what it does is it kind of brings it all together. God bless you. Because as you calculate these limits, your step one always has to be to plug it in. they don't always end up screwing. You know what I mean? Like, they don't always end up being a mess. Case in point, look at the first one. The limit as x approaches 2, step 1 is plug it in. 3 times 2 squared plus 8. 3 times 4 plus 8. This limit here is 20. No nonsense involved. So you don't have to like get crazy with it and freak out about manipulating it until you just plug and chug. Now it's the denominators that cause all that drama. So you're nervous about this one. Don't be, because the limit as x approaches 2 of this is not going to put me in a situation where my denominator is equal to 0. I don't have something funky going on at that point. At 2, that function's defined, no issues. No asymptotes, no holes, no drama. So if you forget to plug in first, you lose an opportunity to see what's going on. Same thing is true here. Everyone sees, oops, what the heck happened there? Everybody sees this 4 and they start freaking out, this -4, and they start freaking out. But you got to do the math, because -4 squared, step 1, -4 squared plus 5 times -4 plus 2 over -4 minus 4 does not give me an indeterminate form. That doesn't give me 0 over 0. -4 minus 4 is -8. I'm allowed to have -8 in the denominator. Nobody cares about that. -8's fine. 16 plus -20 sounds like -4. -4 plus +2 sounds like -2 over -8. Does that give me +1/4? Is that what matches your sheet?
Yes.
So there's no witchcraft involved here. Plug it in. If you plug it in and you get 0 out of 0, that's where the problem is. 3 times -4 plus 12, uh-oh, that's not going to go well. -4 plus 4, uh-oh. Now I have drama. Anytime I get 0 out of 0, when I plug it in, that's where my drama starts. So what I need to do is look at how can I manipulate it, and I've got 3 choices. 4 if you count trig. Factor, find a common denominator, use the conjugate, trig. Okay, so I'll factor it. A 3 comes out, leaving me with x plus 4. Oh, hello, because by doing this, I'm suddenly able to get rid of the problem. That's the hiccup. That's what's screwing everything up. So what I'm left with now is just a value of 3, and that's my limit. Go.
So because you have to eliminate x, so you can eliminate x from the application.
I can eliminate this x here, because when I factor it out, it the hole that is created here disappears.
Also, when it's a whole, it can be
Yep. All right. So I'm not going to do all of these. Oh shoot, this should have been on the next one down. I'm not going to do all of them, but I will encourage you to go ahead and recognize the sign ones. And if there's any drama that you need, anybody that did the homework, I know that just knocks out half of you, that has questions, anything you want to see? Chris? 7. Yeah, how about 7? Can I tell you something about 7? 7 is a great one to do. Thanks for asking on that one. Ready? I need the conjugate. So what the conjugate is going to do is going to allow me to address that radical and square it without giving me a radical, and it's going to allow me to remove it from where my drama is. Step 1 is plug it in. So when I have the square root of 3 plus 1 minus 2 over 3 minus 3, 3 plus 1 is 4, square root of 4 is 2, 2 minus 2 is 0. I get 0 out of 0, and that's not okay. You okay with that so far? All right, so my next step is going to be, if I were to multiply this by the square root of x plus 1, this squared is going to remove that radical. But if I just do this, when I multiply that, I'm stuck with that same radical, so I want it to go away. And what I'm going to use is my sum difference pattern. I know that the sum difference pattern gives me the difference of two perfect squares. So I'm going to multiply it by this value under the radical plus 2, and that's going to, when I FOIL it, first, outer, and last, my outer and my inner terms are going to be a 0 pair, and I'm going to have no radicals. I can't just go around multiplying everything by what I want. I follow the rules of math. So when I follow the rules of math, if whatever I do to the bottom is the same as whatever I do to the top, this function actually, this value here has a value of 1. I'm multiplying it by 1. I'm not changing its value. Anything times 1 is itself. So that's my multiplicative identity. When they taught you the identity property in the 5th grade, they had no idea how much you were going to use it in calculus. All right, first, outer, inner, last. This term times this term is x plus 1, because the square root of something squared is that thing. You okay with that? When I multiply my outer terms, I get positive 2 times the radical. When I multiply my inner terms, I get negative 2 times the radical. There's 0 pairs. See you later, Sally. You don't have to worry about them. When I multiply my last terms, negative 2 times 2 is going to be negative 4. You okay with that? All right. Here's where I went wrong when I was doing this the first time. I then went through and I FOILed my bottom. And when I FOILed my bottom, I missed a factor that I needed to cancel out. So my advice to you, don't FOIL. Don't multiply out. Leave your factors, because then maybe something will be able to be crossed out. That's what you're hoping for. All right. Holy cow, do you see it? I already see it. I'm so excited, because 1 plus negative 4 is x minus 3. Are you okay with that? X minus 3 and x minus 3 canceling out is going to give me my function of 1 over the square root of x plus 1 plus 2. And you're like, nice work, but you still got a radical in the denominator. You're like, it's okay. Watch how it works. I'm going to take my 3 and I'm going to plug it in. 3 plus 1 is 4. Square root of 4 is 2. 2 plus 2 is 4, which puts me back in a position of having the limit once I remove what was screwing it up. Have you ever have like somebody like in a situation you're like, man, that person keeps screwing things up, and then they're gone and it works? So whatever you do in life, whether it's a team or a band, you're like, just get rid of that thing that's not working, and now it works. Grace, does that answer your question? Go.
Number 10.
So number 10 goes into those trig rules that we were talking about. So we're going to have to factor out the sign of x. So the limit as x approaches 0, I'm going to take my sign of x out, and that's going to give me the cosine of x minus 1. Ah, that looks familiar. And then down here, watch what I do. Ready? I'm going to give you an x, and I'm going to give you an x. And the only way that I know how to do that is because somebody told me the rule. And I'm manipulating it, making it work to get there. I know what it's supposed to look like, so that makes it easy for me to do. And now I'm gonna think through my graph. Because this one, I remember that graph meeting at 1, right? And then this one, I remember this graph meeting at 0. Am I allowed to do that? Yes, 0 is a number. 0 is a number. Here he is. He's here. He just can't be in the denominator, which he's not anymore.
Thank you.
What else you got?
Yeah.
11. Oh, I'm totally trig rules. Grace, check it out. Ready? I'm going to take an x out of this, and that's going to leave me with x squared plus 2, right? I'm going to put this sign of x over here because I know what I'm working towards. And then I have this 3. Grace, do you see it now? Isn't he equal to 1?
Oh,
So now when I go to put 0 in, I have 0 squared plus 2 over 3. So my answer is going to be 2/3. Do you see it?
yeah.
All right. In the interest of time, we're going to move on. Okay, so I got this pretty cool statistics, and what we wanted to do was show you why rational functions exist the way they do. So why does a rational function exist the way that it does? And what it is anytime that we are comparing two things using division, we have a ratio. Anytime that we're comparing two things using division, that gives us a ratio. So the National Center for Education Statistics Steve, come on up and hang out with Kenton today. Okay. National Center for Education Statistics keeps careful records of the number of degrees awarded in the United States. The given table shows the number of PhDs awarded to men and women in the United States over time. So we're going to name our two functions, and we're going to let F model the men, and we're going to let G model the women in the terms of the year. So check out these numbers. In 1880, 51 gentlemen earned PhDs and 3 women. 10 years later, almost 3 times the number of men earned a PhD, and 1 less woman. In 1900, the number of men earning a PhD more than doubles. And according to that statistic, you're like, oh, we'll do the women double? So I'm up to 23. 1920, about a fifth. 1940, not looking any better. In fact, by far worse. And then, what? That's crazy. This one here. Look at this jump. What? All right. So what do you notice when you look at the values in the table? What do you think? What do you think? Well, the men steadily increase, right? And the women are definitely increasing, except for that first one. But so significantly more at this juncture here. In the end, check it out. More women are earning PhDs in 2010 than men. Compare that to our 53-to-1 ratio. All right, let's get some data. In 1940, we had 2,861. In 1890, we had 2. So you get how to read the table, right? Now what we're going to do is this is where we get the rational functions. Let H be the function that inputs the year and outputs the value of the ratio of the comparison between the two numbers using division. That is H sub t is equal to F of t over G of t. So that value of H in 1880, and what does it represent in this context? So when I want to find my H function, my H of 1880, I need to figure out what F of 1880 is, and I need to divide that by G of 1880. Talk to your partner and get those numbers. Grab a calculator if you need. So an interesting pattern that we see when we look at the ratio of men to women and how significantly it drops in this phase here, we can look at legislation that was passed. We can look at, and wonder what changed so much that we went from, having a ratio of 73-1 all the way down to having more women than men. So having this rational function is what makes that possible. As T varies from 1980 to 2000, does the value of H increase or decrease? And it's interesting to see the story behind these numbers. And you can look at history to look at the way that legislation was passed to allow women into a lot of higher level learning institutions where they were not prior allowed. Okay, rational functions is defined as the ratio of two polynomial functions. And you're used to seeing the graphs that look like this. The interesting things that we talk about with rational functions are always our vertical asymptotes. And those vertical asymptotes are always going to happen where our denominator equals 0. Our vertical asymptotes are going to be where the graph goes wonky, because right up until it goes 0, it approaches an infinite value, but it happens opposite ways on either side of the asymptote typically. So we end up with these stories where this side is approaching negative infinity, this side's approaching positive infinity. We do have a couple scenarios like this where our asymptotes go up, and we can talk about that limit as it approaches infinity, as that output approaches infinity. Our other conversation that we can have is always going to be our horizontal asymptotes. And our horizontal asymptotes are going to be representing important conversations. And it's interesting, there are some graphs that cross the horizontal asymptote. Not many, but a few special ones for sure. So we can talk about these horizontal limits. And then, of course, our slant asymptotes, where there are graphs where we have no horizontal asymptotes. So our vertical asymptotes are absolute, and our horizontal asymptotes are going to be dependent upon the nature of each of those different functions. So what I want you to do is I want you to just process each of these rational functions. I want you to think about that idea of a horizontal versus vertical asymptote, because that's going to determine our ability to find these limits for sure. Okay. I'm trying to get better at punching holes for you.
Yeah.
Did everybody get? Okay. All right. So today's notes talk about finding limits of rational functions, and it's limits that are involving infinity. So as our x values, we've been talking about x approaching a specific value, whether 0, -1, -2, whatever. Now we're talking about as x gets bigger down our horizontal axis, and we want to look at what is the output approaching as x gets farther and farther to the left or right, depending on if we are talking about positive or negative infinity. So the interesting thing is, and we can talk about each of these graphs, because as my x value approaches negative infinity, where is this graph going? Infinity. So we did this in Algebra 2 when we were talking about end behavior. as x approaches positive infinity, where is this graph going? Yeah. Sometimes the limit as x approaches positive and negative infinity doesn't matter or doesn't match, because as x gets smaller and smaller and smaller, my output of my function could get bigger. As x gets bigger and bigger and bigger, the output of my function gets smaller and smaller and smaller. So go ahead and take a look at these two graphs, and suddenly it's not so simple. With your partner, make some guesses. Surmise where you think this graph is going.
Yeah.
It's approaching zero. Yeah, they're both approaching zero.
All right, so as x is getting bigger and bigger and bigger and bigger and bigger and bigger and bigger, you can see that the graph is now approaching what we know of as our horizontal asymptote. So it's approaching our horizontal asymptote of 1. As x gets smaller and smaller and smaller, it's approaching our horizontal asymptote of -1. So our conversations with rational functions that we used to find those horizontal asymptotes, that's going to come back because, holy snap, it's a limit. Do you know what the most missed answer is here when we ask for what the limit is? Oh, everyone goes, oh, it's 1. What are we approaching as x gets bigger and bigger? What are we approaching as x gets smaller and smaller? Sound okay? So here's some really basics to know. When we do our step 1 of plugging in, let's talk about the value of infinity. When I'm finding the limit as x approaches infinity, bigger and bigger and bigger and bigger and bigger. The bigger my denominator, what ends up happening? The smaller my fraction. So as my fraction gets smaller and smaller and smaller, I'm going to approach a value of 0. And anytime you're curious about that, ask yourself do you want half of the dish of brownies? Do you want 1/10 of the dish of brownies? Do you want 1/100th of the dish of brownies? Do you want 1/1000th of the brownies? If I had a plate of brownies that I was cutting up, I'm asking Jaden how many brownies you want. You're like, hey, I'm gonna take the whole thing. He's like, no, I have to cut it. Sure, there it goes. He's like, okay, I'll take half. Getting 1/1000th of that plate of brownies is gonna be like a little bit crown. The bigger the denominator, the smaller the value. All right, what happens here? If I have 2 to the negative x, isn't that the same as 1/2 to the x? As x goes to infinity, where is this graph headed? 0. So here comes the interesting part that we're going to start looking at, and it's just going to now be about the powers of x. Because this x is to the first power, and this x is squared, and all I want you to think about is just those x's. I don't like the green. Just those x's. If I have infinity over infinity squared, where is the bigger number? They're not the same. Right, but there's more infinity, right? Right? It is, but here's the thing, Pete, and I get what you're saying, but what if I had 3 plus, I don't know, 10 to the 8th, and down here, I had 10 to the 8th squared minus 1. Isn't this going to be, that denominator, a huge number compared? So as I have a greater exponent in my denominator, my limit is always going to be approaching 0, because the value of my number is going to get smaller and smaller and smaller. Sometimes it helps to rearrange the numbers, because the truth is, whatever is coming after the variables doesn't matter. All I care about is looking at my exponents and their coefficients. If I had infinity over infinity, doesn't matter how big my number gets, because it's always the same in my numerator and denominator. That is why when my powers of my x's match, my limit is always going to be equal to the fraction created by the coefficients when the powers match. When the exponents are the same. When we take the time to rewrite and compare and look at where I have more x's, I know that I have more x's in this top. So this is the graph where I have no horizontal asymptotes, but I know that my value is going to grow bigger and bigger and bigger, but this negative sign tells me the graph is going to be a reflection, so that graph is going to grow towards negative infinity. If I need to find a common denominator before I can understand how my fractions work, I need to multiply this by x squared over x squared. And then therefore, I end up with 3x squared minus, 3x cubed minus 1 over x squared. So finding that common denominator allows me to see if I have more x's in my numerator than in my denominator, this is going to grow to be a very, very, very large number as x gets bigger and bigger. So we're doing a lot of this algebraic manipulation because we can't really plug in infinity. So what we're hoping is to get one rational function where we can take a look at the exponents, because what I want you to do is take a cheat and come down and look at this box, because this is what we're working our way towards. The degree of the polynomial is going to determine where your graph is going. If the degree of the denominator is larger, you have a super big number down in the bottom, and your function is headed towards 0. Give yourself an example of a graph that has a horizontal asymptote of 0. As x gets smaller and smaller, or as x gets bigger and bigger, it goes to 0. If the degree of my numerator is larger, then that means there's a super big number up in the numerator, and that means that my graph is growing to infinity. That means that my graph is going to grow up, up, up. If the degree of my numerator and denominator are the same, they're growing equally as fast. So that's when I go ahead and they have a value of 1. So I'm left with looking at the coefficients that are on each of my functions. I'm looking at the coefficients on the terms of the higher power. So let's go back. I can't determine what's going on here until I add my fractions together. So I know my common denominator is going to be x squared plus 1. And then if I factor out an x, I'm going to just need another x. So my powers of my denominator is going to be to the third power. Everyone see how I did that super fast, finding that common denominator? Now when I need to manipulate my top of my fraction, this guy is missing an x. This guy has both an x and an x plus 1, so I wind up with x squared plus 2x squared. Do I have more x's in the numerator or denominator? Is the higher power in my numerator or denominator? I have 3x squared in my numerator. In my denominator, I have an x cubed plus x. Where are there more x's? The higher power is in my denominator, which means this limit is approaching 0. Because it's getting smaller and smaller. Hey, did you know that you could find the limit of each of them separately and add them? You could do that too. The limit as x approaches infinity. Square root of 5. Square root of 5x squared minus 9 over x plus 1. What do you think is going to get that radical out? What do we do? If we squared it, what purpose would that serve? I don't really have a plus minus to get rid of it. Where do I have a higher power of x's? So this is 5x squared minus 9 all to the 1/2 power. Aren't my powers of x both 1? So when I look at my coefficients, square root of 5 is going to be my limit. Okay, so your homework tonight is to try these. Remember what you're doing with the rational function. Any outstanding work you have for me, make sure you turn it in. Do me a favor, get yourself organized. If you need to stay after. If you need to stay after, and borrow my notebook, get caught up and organized, please do so. Alright. Heads up, don't start talking this evening. Hold up. Did everybody get the homework?
Yeah.
Okay. Get organized, get a notebook. We're trying to tell you a story of calculus. And if you're not going back and looking at your previous work, you're missing out. If you owe me the Euler project, I want it. I want it. If you owe me, two